Our last part of the cardiovascular system is going to be about blood. We are going to take a look at what makes blood up, the different components, what are the cellular components, how they are formed, how they are maintained, and then we are going to talk about what is referred to as hemostasis, keeping the blood volume the same. And there are 3 steps to that. We'll take a look at that. And then we'll talk briefly about replacing blood in an emergency. So let's get started. This slide shows you a key thing about blood, and that is that there's a cellular component and there is kind of an extracellular matrix that we call plasma. Now, when we take a look at the difference, most of the blood of whole blood is plasma, about 55%. It has proteins, etc. in it, and that's something you'll see in the next slide. And then there is something called the buffy coat. This is going to have just a little bit of leukocytes and platelets. And then the bottom of this image are the erythrocytes, or red blood cells. And about 45% of whole blood are red blood cells. It's the most dense component. Observe these images and know that we will do our version of this test in our hematology lab. This table really gives you all of the information that you need to fill out the first page or 2 of your note outline. It's all about plasma, how much water is in it, what the plasma proteins are, what other things are in the plasma. And so this one is on you. Use this table to fill out that first part that talks about blood constituents and plasma. Next, let's take a look at these images, and get a feel for the cellular component of blood. As mentioned, we do have erythrocytes, our red blood cells, leukocytes, our white blood cells, and platelets that you see here. We will be looking at slides in lab that are called blood smears, and we'll try to identify all of these structures. The most abundant being erythrocytes, the ones that are a little larger and have staining nuclei are white blood cells, and then these little teeny tiny things that look like pieces of trash. Those are the platelets. We'll talk about each one of these as we go. This image is of hemoglobin, which we'll get to in a minute, but I want you to be clear on the red blood cell, or erythrocyte in general. So the red blood cells make up most of the formed elements by far. They make up 45% of whole blood. So of the formed elements, they're probably about 98–99%. Red blood cells have a lifespan of about 120 days, and the old ones are destroyed in the spleen and in the liver. So let's take a look at red blood cells and their structure first. Red blood cells were probably some of the first cells that early physiologists began to study. And they were perplexed by them because red blood cells don't reproduce themselves. And eventually, when they understood the function of the nucleus in a cell, they realized that this is why red blood cells cannot reproduce themselves. There's no nucleus. So what is in a red blood cell? Well, absolutely no organelles. no mitochondria, nothing like that. There is cytosol, intracellular fluid, and they are full of proteins, and that protein is hemoglobin. So let's take a look now at what hemoglobin is. Hemoglobin is a quaternary protein. It's made up of 4 amino acid or peptide subunits. There are 2 globin chains, beta globin chains here, and 2 alpha globin chains down here. Now, in the middle of each one of these, this is where we find the heme group. So that's where it gets its name, hemoglobin. Okay? Now, the heme group is shown to you here. This is a pigment molecule that has an iron ion in the middle. It is that iron atom or ion that oxygen just has the hots for it. Oxygen binds to the iron in the heme group. Now, it's not the only gas that can bind to hemoglobin. On the globin chains, there are binding sites for hydrogen ions and carbon dioxide. But the dominant gas that is transported is oxygen. So each heme can hold 1 molecule of oxygen. There are 4 heme groups in each hemoglobin, so each hemoglobin can carry 4 oxygen molecules, and there are approximately 250,000 molecules of hemoglobin in each red blood cell. That means that each red blood cell can carry around 1 million molecules of oxygen. That's just great. That is terrific. It really knows how to do its job. Although your textbook does this in a different order, I think it makes sense to talk about the development of the cellular components of blood. And this is referred to as hemopoiesis. You may also see it called hematopoiesis. So this is the process by which stem cells, hemocytoblasts, end up differentiating into the various cellular components of blood. Now, we are going to first look at erythropoiesis in a little bit, which is the production of red blood cells. But let's take a look, and by the way, that is regulated by erythropoietin. So it is the red bone marrow where hematopoiesis occurs. First step is the differentiation of the hemocytoblast into a myeloid stem cell and a lymphoid stem cell. Now, the myeloid stem cell will eventually, after committing to these cells, will end up, and you do not need to know all of these steps. What you need to know is the myeloid stem cell is where 4 of the white blood cells come from: eosinophils, basophils, neutrophils, and monocytes, and also where red blood cells come from, which are not included here. Now, the lymphoid stem cells are what differentiate into the lymphocytes, both B and T cells. So you can see them here. We'll talk about the white blood cells in more detail in a little bit, but let's go into some detail about the red blood cells. Now, again, I'm not going to ask you to remember all of these steps of erythropoiesis. It is important for erythropoiesis to continue throughout your life in the red bone marrow, again, because it doesn't have, a mature one does not have a nucleus. Red blood cells live to be about 120 days. Again, they are destroyed predominantly in the spleen, but also in the liver. The amino acids that make up the hemoglobin and the iron in the hemoglobin are recycled. But if we take that heme group and remove the iron, the result is a product called bilirubin, and that will end up being eliminated from the body in bile. We're going to talk about that more in class. So again, how do we develop red blood cells? As with all blood cells, we start with the hemocytoplast, and that will differentiate through all of these steps. What I want you to note is that starting in phase 3, the nucleus is ejected, and any remaining tissue that is left in the cell is going to be put together eventually in the form of hemoglobin. And at this point in time, this is an immature red blood cell. It's called a reticulocyte. Once the erythrocyte is mature, it is kicked out of the red bone marrow and into circulation. Why does erythropoiesis occur? What is the trigger? Well, let's take a look at this slide and see that the major driver for the generation of more red blood cells has to do with maintaining normal blood oxygen level. Low oxygen is called hypoxia. Now, that hypoxic situation could be caused by low red blood cell count, or normal red blood cell count but low hemoglobin, or a decreased availability of oxygen. There are sensors within the kidney and also a bit in the liver that detect hypoxia. That causes the kidney to secrete erythropoietin. Erythropoietin is a hormone, a ligand, that targets the red bone marrow, and it triggers an increase in the development of red blood cells through erythropoiesis. That results in a larger number of red blood cells that have the ability to carry oxygen, which brings our oxygen levels back to normal. A really good negative feedback system. So this slide again represents normal blood oxygen homeostasis related to red blood cell production. But what happens if it's not normal? What if our red blood cell count is not within our set point? Well, any situation where there is a decrease in oxygen carrying capacity, regardless of the reason, that is referred to as anemia. Now, the flip side of that is when there are too many red blood cells. So way too many of these. And that can be caused by either primarily a tumor in the bone marrow that causes excess erythropoiesis. Secondarily, and this is something we'll talk about in class, and later we'll also see it in the respiratory chapter, that we can see an increase in red blood cell count due to high altitude or chronic lung disease. There is something called relative polycythemia. which occurs when someone is dehydrated. That one is easy to fix. You just drink more water or give fluids IV. Now, another secondary cause of polycythemia could be a problem with blood flow into and through the kidney. The term stenosis means a narrowing, and we talk about renal stenosis. We're talking about a narrowing of the renal artery, so there is less flow going through the kidney, and the kidney detects that as being hypoxic, and it secretes more erythropoietin, EPO, and therefore triggers too many red blood cells. We can touch on these things in class as well. This slide is actually pretty complicated. At the top, it talks about how red blood cells are formed, and then down here, what happens to them. So let's go over this slide in class in more detail. Go ahead and look through it and see if you can follow the basics, but we'll get into some details here for a couple of reasons. One is this relates to the digestive chapter, and we'll be looking at that process later. Now, one more disorder to take a look at, and this is a genetic disorder. Sickle cell anemia is the result of a single amino acid change in the beta chain of hemoglobin, and that completely alters the shape of the red blood cell. So you can see up here, this is a normal red blood cell, this is a sickle cell. The problem with sickle cell anemia is these jagged edges have a tendency to catch on the sides of capillaries, on each other, and that can be an extremely painful condition, as well as if you're not delivering the red blood cells around the body, you're not delivering oxygen and picking up carbon dioxide.